This is a walkthrough of Ms. Volkening's physics class worksheets, circular motion number 2. Alright, so first it says, if you spin a ball at the end of a string and then let the string go, which way will the ball fly? Please draw an arrow to show the direction on the diagram below and explain your answer. Okay, we did this in class. Here's the thing. If you spin this ball, the only reason it moves in a circle is because it's changing direction. And to change direction, that's an acceleration, you must have a net force. So the only reason this happens is because there's some sort of force pulling all the time to make it change direction. In fact, there's this thing called centripetal force. It's always pulling toward the center of the circle, and it's along the string here. Now, if you let that string go, the force is gone. If there's no force, the ball does not accelerate, which means it's not going to change whatever it's doing. So whatever it was doing, when you let it go, it just keeps doing that. So if we let the string go right now, like this is a snapshot, I let the string go right now, the ball will continue on whatever velocity it had. In this case, anything moving in a circle has a tangential velocity. Oh, that was bad. I have to draw this. I usually use a ruler for drawing lines, and I don't have a ruler for this. There we go. Okay, it'll go that way, and if you tip your head, this should be a right angle. The tangent should be right angle with the radius, but I think I'm off a little bit. I'm sorry. It's really hard to, yeah. Usually I turn the paper so it looks nice, but I can't turn the computer screen like that. So it will go in a straight line tangent to the circle because that's what it was doing when it lost its force, so it just keeps doing that. Now it says you are driving around a curve with a radius of 100 meters in a car with a mass of 200 kilograms and a tangential velocity of 30 meters per second. How much centripetal force is needed for you to stay on the road? Okay, here's the thing. For any circle, the centripetal force required to keep your object moving in that circle is equal to the mass of your object times the tangential velocity of that object squared divided by the radius of the circle you're trying to go around in. So this car needs a centripetal force where the car is 2,000 kilograms. The velocity is 30 meters per second. Don't forget to square it. People always forget that. And then the radius is 100 meters. If you put all that in your calculator, you're going to get 18,000 newtons. Oops. Come on. Okay. Flip to the back. If the coefficient of static friction between your tires and the car is 0.9, by the way, kind of an unrealistic number unless it's a race car on a nice dry day. Anyway, is there enough friction to keep you on the road while turning? Explain. All right, here's the thing. For any centripetal force is not really a force in and of itself. It's more like a job done by another force. You need a force to fulfill that job or the job doesn't get done. So in the case of a car going around a curve, the force providing the centripetal force is usually friction, unless we're dealing with a banked curve, and we're not in this case. It's a nice flat curve. Hopefully it's dry. So we have to figure out, well, how much friction is there? Okay, friction is mu times the normal force. Okay, in this case that's 0.9. The normal force, as long as this is a nice flat surface, then the normal force is actually the same as the force of gravity, so m times g. So what I have here is m, which is 2,000, times g, 10. So I end up with 0.9 times 2,000 times 10, that is 18,000 newtons. So this is the maximum amount of static friction that's available, and I needed exactly that much. So what I have here is the friction is exactly equal to the centripetal force. Oops. So yes, the car will stay on the road because I have the force necessary to fill the job of centripetal force. Barely, but I've got it. Okay? Basically, as long as the friction is greater than or equal to the centripetal force, it's gonna be fine. Okay? So number 4, what if it starts raining and the coefficient of static friction drops to 0.5? Then will you stay on the road? Well, doing number 5. Oh, that's number 4. Sorry. Doing number 4 now. Well, now the friction is 0.4, or not, 0.5. Why do I, wow. Okay, it's 0.5 times 2,000 times 10. Okay, if I do that, I end up with 10,000 newtons. In this case, the friction is less the centripetal force that's necessary. I still need 18,000. It's the same curve and the same car and the same speed and everything. So that's not enough. That's not enough to fulfill it. I'm not going to stay on the road. I'm not going to stay on the curve. I'm not going to stay in the circle. And the road goes on the circle, so I'm not going to stay on the road. That's bad. What could you do to stay on the road? Well, there's two things that, like, what I need this to happen. The friction needs to be greater than the centripetal force. So either I've got to raise the friction, or I've got to lower the centripetal force. Well, raising the friction is kind of impossible, because to do that I need to either up the coefficient of friction or up the normal force. Neither of which is really in my control at this, when I'm out driving, okay? So what I need to do is I need to decrease the centripetal force necessary. Well, if we go back to the equation, if I want to make this number smaller, I could either make the mass smaller, again, not something I can really do right now. I could make the radius of the curve bigger, again, not something I can really have the power to do because that involves moving the road, or I could make the velocity smaller. Well, that's something I could do. That means just slow the heck down. Just slow down, people. Slow down. And that's why you're supposed to, it's one of the reasons, there's actually a lot of reasons, but that's one of the reasons you should slow down in the rain, because you're going to be losing some coefficient of friction because it's slippery, and curves are going to have less friction, and so you need to bring down your centripetal force that's necessary to make those curves, and therefore the only thing you can really physically do is slow down. So please slow down in the rain.